Friends, I welcome you on BYJU'S Exam Prep, India's most comprehensive preparation platform for all the engineers. So the candidates who are joining me live, just quickly confirm your presence in the comment section and tell me whether my audio visual quality, everything is clear so that we can start with the session. A very good afternoon to all of you. Welcome to the session. Hi Raghu, how are you? Welcome to the session. So just quickly confirm your presence in the comment section and tell me about the audio and visual quality. And let me just brief you what is the ideal duration and what is the agenda for today's session. You must be aware that in this session, we are going to start one of your core subject, that is electrical machines. Myself, Ashutosh Saxena, and along with me, Ashu Jhangra sir is going to take this complete subject. Today, I will be taking the complete session for 4 hours approximately, 5 to 9 you can say. And I will be taking care of transformers, and induction motor. So these two topics I will be covering, and DC and synchronous is going to be covered by Ashu Changa sir. I'm fine, Raghu. Good evening, Satya. So let us start this session. Today is the first part. Okay, the actual timing was 4 p.m. but because I was having another session, that is why it was being rescheduled to 5 p.m. But tomorrow, when Ashu sir is going to take the session, then it is going to be started at starting at 4 p.m. only. Okay. So let us quickly start. Some of you may be joining me for the first time. So there is a brief introduction about myself. My name is Ashutosh. As you can see on the screen, I have 11 plus years of teaching experience, completed MTech from IIT in 2010, written a couple of books, and these are my areas of expertise. All the candidates who are joining me live, just quickly hit the like button, hit the bell icon, and subscribe to BYJU'S Exam Prep so that you do not miss any of the important session for your examination. You all must be aware that currently we are in the Maha Marathon series, that is a GATE 2023 booster series, where electrical, electronics, instrumentation, and computer science, all these engineering streams, all the syllabus is going to be covered within just 12 days. A lot of subjects already we have covered. So if you have missed these sessions, do attend. I think I forgot my mic. Just give me one moment. And you are not telling me that my voice is not clear. Okay, just give me a moment. Yes, good evening, Sudarshan. How are you? Welcome to the session. Now, audio and visual quality, everything is clear? Now voice is okay? Okay. So this is the Maha Marathon series. You all must be aware, for electrical, electronics, instrumentation, CSNIT, all the subjects are being revised in just 12 days. A lot of subjects already we have completed. So if you have missed these classes, do attend these sessions. These are going to be quite important for your GATE 2023 examination. Now, everybody's favorite and my favorite, Abhinav Negi sir, MTech from IIT Delhi, more than 11 years of teaching experience. He is going to conduct a mega workshop on 7 success mantras from a beginner to a topper in GATE 2024. So if you have a junior, if you have a colleague, or you yourself are interested in GATE 2024, then you can attend this mega workshop on 15th of January, right, 12:30 p.m. in the afternoon, but you have to get yourself registered to attend this workshop. Now, the legendary faculty for aptitude, Rakesh sir, is going to come with general aptitude, 15 marks in just 15 hours. So stay connected. It is going to be a very important session for you. Rakesh sir and Ankit Joshi sir, both the legendary faculties for mathematics, they are coming with the session Nothing is Impossible, a non-stop maths marathon in which the complete syllabus for maths is going to be completed within 2 days only. So stay connected to all these wonderful sessions for your examination. Now, one more important information about the GATE and EAC test series on BYJU'S Exam Prep, where you will be getting the complete unlimited access to the full-length mock subject test. The link is given in the description that you can follow. Some of the important features of this test series is 60 plus tests covering GATE and EAC, detailed mock analysis, virtual scientific calculator, 4,000 plus practice questions you will be getting. You will be getting all India open mocks, and all this is being curated by the GATE experts. Yes, you will be getting verbal aptitude also. You will be getting the PDF. Actually, because of some health issue, I could not do it. But today after the session, I will give you both the PDFs. Okay, PDF for power system part 2 also and for machines also. Okay, don't worry. So we'll be starting with transformer. But before I start, let me give you some brief idea that what are the important topics from which you can expect questions in the GATE examination. The first thing is transformer action. What is transformer action? You must know. Then equivalent circuit of the transformer. You may get the question. Third, you will get questions from voltage regulation and efficiency of the transformer. Then you can get question on Scott connection and open delta connection, apart from other three-phase connections for three-phase transformers. Okay, open delta connection, you may get a question. This year there is a high possibility for getting a question from these areas. And last but not the least is the parallel operation of transformers. So these are the important areas you must revise. Is it clear, everybody? So I will try to touch upon all these topics with the help of the questions, because you can understand for electrical machines, it is not possible to completely justify each and every part of the subject within this short span of time. So what my agenda is with the help of the questions, I will try to touch upon all these issues. Okay. So before I start with this, let me just give you some brief idea about this, about the transformer, and then I will discuss the questions. Is it clear, everybody? That is sufficient, I think. One more point I want to add here, that is auto transformer. You may get a question. Just add auto transformer also. That is also important for this year, I hope. Okay. So if you talk about the transformer, you all must be aware, if we talk about a two-winding transformer, so voltages you can take as V1 and V2, both the sides. Currents you can take as I1 and I2. And the number of turns of primary and secondary, or input and output, you can say is N1:N2. Now this transformer, how it is going to operate? The basic idea of transformer is that one side of the transformer you are going to connect a source, okay, to supply the load, and the other terminal you are going to connect a load. This is the basic idea. Okay. How this source connected at one side or one terminal is going to deliver power to the load connected to the other terminal, that is possible because of the magnetic coupling between the primary and the secondary windings. For example, let us take this simple construction of the transformer. Suppose this is the source side or primary side, and this is the load side, or you can say secondary side. So this is load. This switch is open right now. This is your source, and this switch is closed. So this voltage source is definitely going to supply some current here in this winding, and the current in this winding is going to be, suppose, flowing in this direction. Let me use this color. So at any point of time, because it is going to be alternating source, so the current is also going to be alternating, changing its polarity between positive and negative. The current is flowing in this primary winding. Suppose the number of turns are N1. So what will happen? In the primary winding, you will be getting a MMF, that is N1 I1. This MMF is going to establish a time varying flux in the core of the transformer, something like this. Now for this given direction of current, this MMF is going to establish a flux where fingers are moving in the direction of current and thumb is going to give you the direction of established flux. So it is going to be like this. This flux is a time varying flux. It is visible. This color is visible, I hope. Okay. Now if the secondary is not connected, if the switch is not connected, load is not connected to the circuit, so what will happen? Because this flux is a time varying flux, both the primary and the secondary winding, some EMF is going to be induced. Suppose this is E1T here and this is E2T here. Okay, this is going to be the instantaneous values of E1 and E2. Because the secondary side load circuit is not completed, so current is going to be 0 in the secondary circuit, but the primary side, it is going to have the current. And why you are getting E1 and E2? It is because of the Faraday's law of induction, that whenever a time varying flux is linked with the winding, some EMF is induced. The polarity of E1 and E2, how it is being decided, that is one important concept in transformer. The polarity of E1 and E2 is decided as, if you give full freedom, a complete opportunity for E1 to circulate its own current, then it will circulate its own current in such a direction so that it can oppose its own cause as per the Lenz's law. So given an opportunity, E1 and E2 will circulate a current so as to oppose their own cause. For example, if you forget about this voltage source and suppose it is short circuited and E1 is given an opportunity to circulate its own current, then what should be the direction of current for E1 given an opportunity? It should be in this direction. Yes or no? It should be in this direction. Why? Because it wants to oppose its own cause, that is IT or VT. So if this is the direction of current flow for E1, then at this time instant E1 is positive here and E1 is negative here. The positive and negative polarity is decided like this. In the same way, if you give full freedom, an opportunity to E2 to circulate its own current, how it is possible? You short circuit this, close the switch, then what will happen? E2 will circulate its own current in such a way so that it opposes its own cause. Now what is the cause for E2? The cause for E2 is the time varying flux. So if it flows the current in this direction, it will have a flux in the secondary winding which is going to be opposite to the flux in the core. Flux in the core is downward for the limb, for this limb for the secondary, but for the current sense, if you give an opportunity, it is hypothetical. We are just trying to get the polarity of E1 and E2, then fingers moving in the direction of this hypothetical current, the flux is going to be upside. I hope you are getting this. So at this instant, E2 is positive here and E2 is negative here. So you see this E1 and E2, the same terminal is going to be positive or negative, and that is why we say for the transformer action, subtractive polarity is required. Subtractive polarity is required for transformer action. Is it clear for everybody? Okay. Now, for transformer action, we have a dot convention. That dot convention says that, let me take another diagram, otherwise it will be quite confusing. It says and suppose this is the secondary winding, but it is open circuited, not connected right now. So there is going to be a flux in the core like this. Okay, if this is the direction of current, now the dot convention for the transformer action is that if the current is going to enter the dot at this winding, then it should be leaving the dot at this winding. If the current enters the dot at one winding, then it is going to leave the dot at the other terminal, or vice versa. If it is leaving the dot here, then it is entering the dot here. Now this is important to get the polarity. So let me give you one example. I hope you will be able to do this. This type of question can be asked in the GATE examination. Sometimes you are reading big things, and in the GATE examination they are asking very fundamental questions. Suppose this is a transformer core where one winding, the source is connected, and there are other windings like this, which are going to have some load. Now for all these windings, you have to tell how you are going to place the dot when all these are going to have some load connected to them. Suppose this is 1 dash, this is 2 dash, this is 3 dash, this is 4 dash, this is 5 dash, this is 6 dash, this is 7 dash. So suppose you are placing the dot here when the current enters at the source side. If the current enters at the source side, the current is going to be flowing in this direction. So there will be some MMF, and this MMF is going to establish a flux in the core in this direction. Is it clear, everybody? Okay. Now in all these windings, the current direction is going to be such that it is going to oppose its own cause as per the Lenz's law. So if you see this winding 2 dash, the winding is going to have a current so that it produces a flux which is opposite to this flux. So the main flux or the flux in the core is left to right. So this 2 dash must be having a flux which is right to left. Just see the fingers movement direction. The fingers movement direction is from downward to upward, So the direction of current in this winding is going to be something like this. It is coming from here, it is coming from here. Now, if the current is entering the dot here, then the current must be leaving the dot here. So you should place the dot here. This is how you are going to identify the dot. Similarly, for 3,3 dash also, you must have the flux going from right to left, because it should oppose the main flux in the core. So what is the direction of current? Downward to upward. Downward to upward. Downward to upward. Current is entering at the source at the dot, so it should leave the dot at the load side. 4,4 dash. The main flux in the core is going from top to down. So the flux because of the current in 4,4 dash should be upside. Yes or no? Downward to upward. So what is the finger movement? It is left to right. It is left to right. Similarly for 5,5 dash also, left to right, left to right. So current entering at the source at the dot. So at the load, it must be leaving the dot. It must be leaving the dot. 6,6 dash and 7,7 dash, the flux is going from right to left. So the currents in these windings should be such that it generates or produces a flux which is going from left to right in this direction. So what is the direction of fingers movement? It is upward to downward. It is upward to downward. Okay. So current leaving the dot at the load side, current leaving the dot at the load side. This is how you are going to decide the dots if multiple windings are given. Is it clear, everybody? Are you able to follow this? Just tell me yes or no in the comment section. Okay. Now let us see the equivalent circuit of the transformer. This is the supply voltage V1. This is the load side, secondary winding, you can say. Okay. So it is going to have a voltage V2 here. Now, suppose the current here is I1. Okay. Current here is I2 dash. We'll understand what is I2 dash. Just give me some time. This is the no load current at the primary no load current. This I0 has two components, the core component, core loss component, and the magnetizing component. This is RC, this is XM. Okay. This is R1, this is JX1. And this is going to be R2, this is going to be JX2. Okay. And the number of turns are suppose going to be N1 is to N2. Now the first thing you have to understand, and the current here is going to be I2. Current here is I2. So these two windings now of the transformer, they basically represents an ideal transformer, because all the losses you have separated. How you have separated the losses? R1 represents the copper loss in the primary winding. What this X1 represents? X1 represents the equivalent reactance for voltage drop due to primary leakage flux. Primary leakage flux. What is primary leakage flux? Primary leakage flux is the flux which is only linked with the primary winding, not with the secondary winding. What is secondary leakage flux? It is the flux which is linked with only with the secondary winding, not with the primary winding. And what is mutual flux? Mutual flux is the flux which is linked with both the windings. This RC represents the core losses. Okay. XM represents the magnetizing current required for the magnetic coupling. R2 represents the copper losses in the secondary winding, and X2 again represents the equivalent reactance for voltage drop due to secondary leakage flux. Secondary leakage flux. So basically now this part of the transformer winding, they represent the ideal transformer, because all the losses you have separated and what is remaining is the ideal transformer. Now I want to make you understand what is this I2 dash, then solving the problems will be easy for you. Now suppose this is your transformer. This is the primary winding where you are going to connect the source. Source is connected, AC source is connected. And here you have the secondary winding, you are going to connect the load. Okay, this switch is open right now. So once again, let us start from 0. This is the voltage source you have connected to the primary, so it will circulate some current I1. This I1 current is flowing with N1 number of turns. It will give rise to N1 I1. Okay. Now suppose I am calling this current as I0. Why I0? Because right now I have not closed the switch at the secondary side. So this I0 I am calling as the no load current. No load current. Right now I am calling it as the no load current. So N1 I0 is going to be the MMF, and this is going to establish a flux in the core phi, which is going to give rise to E1 and E2 at the primary and secondary side. Now this is the story till now what we have. Now if you connect the load to the secondary circuit, you close this switch, what will happen? Already E2 is there. E2 EMF is already there. So if you close this switch, certainly there will be some current. Suppose this current is I2. If you close this switch, the current which is flowing in the secondary circuit, suppose it is I2. This I2 current flowing here will have its own MMF, okay, that is N2 I2. This N2 I2 is going to establish a flux which is going to be opposite to the flux in the core. Suppose the flux in the core is like this. This is the flux in the core. Okay, now this N2 I2 will generate some flux which is going to oppose this main flux in the core. But the flux in the core cannot be reduced. Why? Because this flux is not being decided by this winding, it is being decided by the source connected to the primary, and you cannot change something which is not controlled by you. Yes or no? How you can change it? Because this circuit is going to generate a flux which is opposite to this flux in the core, but this flux in the core cannot be reduced. It means some extra current must be taken from the supply to compensate this flux or this MMF N2 I2. So I am assuming the current which is drawn by the source, extra current, is going to be I0 plus I2 dash. This total current we are calling as I1. I hope you are getting this. So now you get the idea about what is this current I2 dash. This I2 dash current is the current which is the extra current taken from the primary to compensate for N2 I2. Now with this, now I can write the MMF balance equation for the transformer. It says the total primary MMF N1 I1 has two responsibilities. Number one, to balance or counter the secondary MMF N2 I2 plus to establish flux in the core. Okay. Now suppose you want to write what is I1. So just take N1 to this side. So it becomes N2 upon N1. This is I2 plus I0. Now this N2 upon N1 I2 we are calling as I2 dash. So I1 is I2 dash plus I0. Is it clear, everybody? I0 is the no load current. I hope it is clear for everybody. Now, when you are going to solve the problems for transformer, you have to refer the circuit most of the time to the primary side. Most of the time you have to refer the circuit to the primary side. So the final equivalent circuit that you are getting is something like this. This is load side voltage, terminal voltage V2. This is V1. This is primary current I1. This is the no load current I0. This is RC, core loss component IC, magnetizing component I mu. This is XM. This is R1. This is X1. This is R2 dash, and this is X2 dash, and this is V2 dash. Now E1 and E2, if we are writing in terms of the RMS values, so this is your E2 dash and this is your E1. This is your E1. So you can understand E1 is equal to E2 dash. E1 is equal to E2 dash. In general, this is your equivalent circuit for the transformer. So, if you observe, when we have referred the secondary to the primary, referring secondary to the primary. So, how you are referring, let me just give you some idea. How you are writing E2 dash. Let me add some more pages here. 2-3 pages I require. Just after this we are going to start, don't worry. Just some idea I want to give you so that you have the same understanding how we are going to discuss things. Now how we are writing, let us first understand how we are writing E2 dash. E2 dash you have to rationalize from where you are coming from secondary side. So secondary side number of turns is N2. To where you are going to the primary side number of turns is N1. So this is how you are going to write E2 dash. Is it clear? How you are writing I2 dash? Again I2. Now I2 you have to reverse it. I2 you have to reverse it. Okay, N2 upon N1. So it is going to be N2 upon N1. What you are doing for E1, E2 dash, you have to reverse it for I2 dash. How you are writing for R2 dash? It is going to be R2 from where you are coming secondary side, so N2, to where you are going primary side, do the square. X2 dash from where you are coming secondary side to where you are going primary side, do the square. How you are writing V2 dash? Write V2 from where you are coming secondary side to where you are going, primary side. The only thing you have to remember it for the current. Current is going to follow the reverse rule as you are following for EMF. Is it clear, everybody? Now, when you are solving the question for efficiency and nothing is given in the question. Suppose you are solving the question on efficiency and nothing is given in the question, then you can use this approximate circuit. You can shift the shunt branch like this. And this circuit you can use. Again, secondary refer to primary V2 dash. This is RC, this is XM, this is V1. Again, this is I1, this is I0, this is I2 dash, this is R1, this is X1, this is R2 dash, this is X2 dash, this is V2 dash, this is I2 dash. This is how you are going to use when it is for efficiency. If nothing is given in the question, you can follow this equivalent circuit. The reason being, by using this, you have separated the core losses and the copper losses. R1 and R2 dash together are going to represent the total copper losses of the transformer, whereas RC represents the core losses. And if you want to solve for the voltage regulation, you can use this equivalent circuit. You can ignore the shunt magnetizing branch. Okay, you can ignore the shunt magnetizing branch. Okay, this is R1, X1, R2 dash and X2 dash. Okay, because voltage regulation, you are more interested in the series voltage drop rather than in the shunt branch. So there will be some error, but approximately you can use this. You will get very close result if you use this circuit. So this is about the basic idea about the transformer. Now let us start with the questions. Is it clear, everybody? So this is a very basic fundamental question. This question will give you a complete idea and will remove all the confusion in your mind that if a transformer question is going to come, how you are going to proceed. Let us try to understand. He is saying to find the parameters of the equivalent circuit are given. The transformer is 150 kVA. It is 150 kVA, 2400/240 volts. It has R1, R2, X1, X2 is given, RC is given, XM is given, 0.8 power factor lagging. Okay. The circuit is referred to the primary. This is also given. Let me just, something is missing in this question, so let me add that. I don't know why the options are missing, so let me just give you options also. It is going to be a multiple select question. Okay, so option A is primary voltage is 2454.68 angle 0.69 degrees. Primary current is given as 63.65. Angle is minus 37.86 amperes. Primary power factor is it is 0.7821 lakh, 0.7821 lakh. And option D is none. So it is a multiple select type question. How you are going to proceed? So let me just first draw the circuit, refer to the primary. Circuit refer to the primary is going to be like this. Already we have discussed it. This is the shunt magnetizing branch, and this is the secondary refer to the primary. This is V2 dash, okay. This is R2 dash, this is X2 dash, this is R1, this is X1, this is RC, this is XM, this is V1, this is I1, this is I0, this is I2 dash, this is IC core loss component, this is the magnetizing component, okay. And you have E1, EMF induced to the primary side, and E2 dash, EMF induced to the secondary side, refer to the primary. The first thing you have to understand is when the rating of the transformer is given like this, what is this 240 volts? Okay, I'm getting a question here. Sudarshan is asking what is the difference between turns ratio and transformation ratio. See, in general, if you see the turns ratio and transformation ratio, both are same thing. Okay, when you say turns ratio, so you are specifically mentioning about N1 and N2. But when you say transformation ratio, so it varies. It depends how the statement is being framed. For example, if you see here, we are going to take the turns ratio, the transformation ratio as 2400/240. Yes or no? 2400/240. But this I am not taking as E1 and E2. That is what I am trying to make you understand. This 240 I am going to take as the secondary terminal voltage. Are you getting this? V2 is going to be 240 volts. Very, very important thing. A lot of people confuse in this. Even though we are going to take the transformation ratio as 2400/240, but we are not taking it as E1 and E2. We are taking it as 240 volts as V2. Okay? Are you getting that? Just tell me yes or no. Is it clear, everybody? Now, what I'm going to do is first with the help of V2 dash and I2 dash. What is I2 dash? Do you have any idea about I2 dash? Yes. I2 dash you can write because the rating is mentioned, and V2 you are taking as 240. So can you tell me what is I2? What is I2? It is 150 kVA divided by 240. And what is the angle by which it is lagging? It is 0.8 power factor lagging. So this is going to be minus of cos inverse 0.8. Can you tell me what is this value? Just solve this fast. What is I2 you are getting? Just tell me fast. Use your calculators. See, today you should not do laziness. You have to be a little more active. Okay. 625. So I'm assuming it is correct. 625 angle is minus 36.86 degrees. This is the current I2. Now I want to find what is V2 dash. So it is going to be V2 from where you are going, N2, to where you are going, N1. What is V2? 240. Only in terms of magnitude I want to see. What is N2? Now see, N1 is to N2 is going to be like this, 2400/240. So it is 240 and this is 2400. So it is going to be 2400 volts. Is it clear, everybody? What is I2 dash? It is going to be I2, and instead of N1 upon N2, it is going to be N2 upon N1. So I2 is 625, N2 is here 240, N1 is 2400. So it is going to be 62.5 amperes. Just the magnitude I am saying. So now by using this circuit, can I write E2 dash, writing the KVL equation? So you can write E2 dash. It is going to be V2 dash plus I2 dash. Now you have to write R2 dash plus JX2 dash. Now what is R2 dash? R2 dash is R2 N2 N1 whole square. So what is R2? R2 is given as 2 milliohms. It is 2 milliohms minus 3. N1 is to N2 is going to be 2400 upon 240, that is 10. So 10 square is 100. So it is going to be 0.2 ohms. What is X2 dash? It is X2 N1 upon N2 whole square. What is X2? X2 is 4.5 milliohms. It is 4.5 milliohms multiplied by 100. So it becomes 0.45 ohms. So just put all the values. You know what is V2. You know what is V2 dash, what is I2 dash. Just put the values. You can solve it later on. If you want, you can solve it now also. I will give you the data from my reference. You must be getting E2 dash as 2426. Okay, 2426. I'm writing here. Please confirm this. 2426.92, and angle you must be getting as 0.35 degrees. 0.35 degrees. Okay, say this is equation number 1. Let me add some pages here. It's going to be a lengthy question because it's for your understanding. But this type of question, one question equals to 10 questions you can understand. So it is better to invest this time right now with all your patience. Okay. Now suppose you are getting E2 dash. E2 dash is going to be same as E1. E1 and E2 dash is going to be same. So this is going to be same as, E1. Yes or no? Now you know E1. If you know E1 or E2 dash, can you tell me what is IC and I mu? Because you know what is RC, what you know what is XM. So what is going to be IC here? What is going to be IC here? IC is going to be E1 divided by RC. What is going to be I mu? It is going to be E1 divided by JXM. Can you solve this? To solve this, as per my reference, you must be getting it IC as 0.2427. 0.2427. Angle you must be getting 0.35 degrees. 0.35 degrees. And what is I mu? As per my reference, it is 1.5658. 1.5658, and the angle is going to be minus 89.65. Minus 89.65 degrees. The moment you get the core loss component and the magnetizing component, you can write what is the no load component. It is IC plus I mu. Just add it up and you will be getting I naught. I naught is going to be, as per my reference, I naught is going to be So just add it up. I don't have a reference value for I naught. Okay. You can solve it. What is the value you are getting for I naught? Once you get I naught, can you write I1? Yes, it is going to be I naught plus I2 dash. I2 dash, you know, I naught you have just found. So I1, I have the reference. I1 is coming as 63.65. 63.65. Angle coming is minus 37.86. Minus 37.86 degrees amperes. The moment you get I1, now everything is clear. Just by applying the KVL in the primary circuit, you can write what is V1. So what is going to be V1 now? V1 is going to be E1 plus I1 R1 plus JX1. E1 is nothing but E2 dash. You know what is the value. I1 you have just calculated. R1 X1 is given in the problem. So you can calculate this also. I'm just giving you the reference. You can cross check it later on. I hope you understood the process. Okay. So Raghuram has found it is 1.58 angle. Please confirm these values, friends. Okay, you have found I mu. I mu or... Okay, this you are telling as I naught, 1.58. Okay, you cross check it, whatever comes. So V1 as per my reference, you must be getting 2454.68. 2454.68 angle, you must be getting 0.69. 0.69 degrees volts. What is I1 you have got? I'm writing here so that you can find the power factor. It is 63.65. 63.65. Angle is minus 37.86. Minus 37.86. This is ampere. So two options you can match from V1 and I1. Okay, magnitude. And for power factor at the primary side, it is going to be cos of, because this is negative, this is positive, so you have to add it. So it is 37.86 plus 0.69. If you solve it, the power factor you must be getting is 0.7821 lakh. Is 0.7821 lakh. Is it clear, everybody? Yeah, this question is actually equivalent to number of questions. A part of this question can be asked in your GATE examination, but this complete picture is very important to understand what is happening and how we should be proceeding. So what is the correct answer you are getting? What is the correct answer you are getting? So because it is a multiple select question, primary voltage you are getting like this. Primary current you are getting like this. Okay. And primary power factor. So all these A, B, C options are going to be correct. Is it clear, everybody? Okay. So let us see the next question. The next question is, if applied voltage of a certain transformer is increased by 50%, so the voltage is being increased by 50%, suppose V2 becomes 1.5 times V1 because 50% it is increased, and the frequency is reduced to 50%, so the frequency is reduced, so it becomes 0.5 of the first case, assuming that the magnetic circuit remains unsaturated. Okay. Magnetic circuit remains unsaturated. The maximum core flux density will change to. So what is this maximum core flux density? Let us understand. Suppose you are writing the RMS value of the EMF induced in the primary side. It is root 2 pi f pi and number of turns is N1. Similarly, for the secondary side, E2 is root 2 pi f pi N2. Whether it is E1 or E2, if you compare it, you will see V1 is going to be directly proportional to E1. Yes or no? Because the difference between V1 and E1 is nothing but R1 and X1 voltage drop. You just close your eyes and remember the equivalent circuit. So the difference between V1 and E1 is nothing but the voltage drop R1 and X1, if you remember this. See the equivalent circuit. V1 and E1, the difference is R1 and X1. Now R1, the resistance of the primary winding. If it is a winding, if it is an inductive winding, resistance is going to be very less. And X1 represents the leakage flux. Leakage flux is also going to be very less because you are using concentric windings. Yes or no? So in case of transformer, leakage flux is very less. It means very effectively you can say V1 is approximately same as E1. So can I write, I'm talking in terms of V1, E1. V1 is directly proportional to, this is a constant, this is a constant, this is frequency, this is flux, this is number of turns N1, this is also constant. So this is frequency and this is flux. Flux you can write as flux density B, and this phi is actually phi m. Please understand this. This phi flux, this is the maximum value of the sinusoidal flux, okay, that is in the core. So this phi m is going to be Bm and the cross-sectional area of the core. Cross-sectional area of the core is going to be a constant, so phi m is directly proportional to Bm. So you can write V1 is directly proportional to F into Bm, or Bm you can write as directly proportional to V1 upon F, or in simple you can write Bm directly proportional to V by F. So you can write Bm2 upon Bm1, it is going to be V2 upon V1, and this is going to be F1 upon F2. V2 is 1.5 times V1 and F2 is 0.5 times F1. So simplify this, you will be getting Bm2 as 3 times Bm1. So what is the correct answer? The maximum core flux density will change to 3 times. Is it clear, everybody? Are you getting this? Okay. See the next question. Okay, next question, nothing is coming. Okay, maybe there is some issue. Okay, just leave it. Okay, maybe some formatting issue. Just see this question. This question belongs to the open circuit and the short circuit test. Okay. Now, open circuit test and short circuit test is one of the most crucial area from where question can be asked. So you understand, when it is open circuit test, your circuit becomes like this. Forget about other components because it is only going to represent the core losses. So this is V naught, this is I naught, this is RC, this is RC, and this is XM, where this is IC and this is I mu. Now, if you understand the relation, IC is going to be I naught cos phi and I mu is going to be I naught sin phi, where phi is the no load power factor angle, where phi is the no load power factor angle. Is it clear, everybody? Now, let us see what is the data given for the open circuit. For the open circuit test, the voltage is given as 2300 volts. The current is given as I naught is given as 0.21, and the total loss, this is nothing but the no load loss, that is the core loss, 50 watts. Okay. So suppose P naught is given as 50 watts. Okay. V naught is given as 2300 volts, I naught is given as 0.21 amperes. The moment you find IC and I mu, it is very easy. You can find what is going to be this RC and XM, yes or no? So what is IC? You can write IC, you can write as I naught cos phi, which is nothing but P naught upon V naught, yes or no? So what is P naught? Is given as 50 watts. What is V naught? Is 2300. Just solve this. What you are getting as IC? What is the value you are getting for IC? As for my reference, it is 0.02174. 0.02174 amperes. You know what is I naught, you know what is IC. Can you tell me what is I mu? Yes, it is going to be I naught square minus IC square. What is I naught? It is 0.21. So 0.21 square minus what is IC? It is 0.02174 whole square. Just solve this. You will be getting I mu. As per my reference, you must be getting it as 0.20887. Just cross check it. 0.20887 amperes. So you got the IC and I mu. The moment you get IC and I mu, your life becomes easy, because now you can directly write what is RC. RC is going to be V naught upon IC. Yes or no? Yes. And what is XM? It becomes V naught upon I mu. In terms of magnitude, I am saying, just solve these, and I think you must be getting RC, you must be getting as 105.8. 105.8 10 to the power 3 ohms. 10 to the power 3 ohms. XM, you must be getting as 11.011. 11.011 10 to the power 3 ohms. Everybody is getting that? Okay. So I'm getting a lot of reflection, so I hope it is visible for you. Okay, what is written on the board is visible for you. Okay. Anyways, so now with the open circuit test, you have found the shunt branch element, that is R0 and XM or X0. Now for the short circuit test, how you are going to proceed? For the short circuit test, this is the voltage applied. In case of short circuit test, this is the current, this is R equivalent, and this is X equivalent. What is this R equivalent, X equivalent? Let me just write it for you. R equivalent, if it is referred to the primary side, in general we are referring to the primary side, this is R1 plus N1 upon N2 whole square, this is R2. And what is this X equivalent? It is X1 plus N1 upon N2, this is whole square, and this is X2. Now whatever power loss is going to be there, that power loss is going to be only in this R equivalent, because X equivalent there can be no power loss. So what is the power loss in case of short circuit? That represents the copper losses. So that is given as 160 watts. This is 160 watts. The voltage is given as 47 volts. 47 volts, and current is given as 6 ampere. Current is given as 6 amperes. So this power you can directly relate, yes or no? And you can get what is R equivalent. So what is going to be R equivalent? It is going to be total loss in case of short circuit test divided by it is going to be ISC square. Yes or no? Because this represents the copper loss. It represents the copper loss. So what is the value you are getting for R equivalent? I think you must be getting it 160 divided by 6 square. So as per my reference, you must be getting it 4.44 ohms. 4.44 ohms. Now, how you can write Z equivalent? Because if you remember the circuit, then problem becomes very easy for you. This is total Z equivalent now. So what is Z equivalent? Z equivalent is going to be VSC upon ISC. So this is VSC upon ISC. This is 47 divided by 6. As for my reference, you must be getting it 7.833. 7.833, and this is ohms. So can you tell me what is X equivalent? It is simply going to be Z equivalent is square minus R equivalent is square. Just solve this. I think you must be getting, as for my reference, 6.45. 6.45 ohms. So what is the correct option? Now you can cross check. A is the correct one, I think. So A is the correct one, yes. A is the correct one. Everybody is getting that. So next problem is quite easy problem. I think you all can do it on your own. Simply apply the voltage regulation equation, formula based question. Don't apply your brain. Already you have very less of it. R per unit cos phi plus minus X per unit sin phi. Okay. R per unit is given, I think. So ohmic loss represented as 1%. So it represents R per unit. It is 0.01. What is cos phi? It is 0.8. And because it is lead, so positive you are using for lag, negative we are using for lead. So negative you have to use X per unit. The reactance drop is 5%. So it gives you X per unit 0.05. If cos phi is 0.8, what is sin phi? It is 0.6. Just find it. I think you must be getting minus 2.2. Yes or no? So what is the correct option? D is the correct option. D is the correct option. D is the correct option. Let us see the next question. Next question also, I think, yes, you all can do it. Easy question. A 50 kVA transformer has a core loss of 400 watts. Just a moment. Yes, sorry for that. So 50 kVA transformer has core loss of 400 watts. So it represents core loss. And full load copper loss, PCUFL, that is full load copper loss, is given as 800 watts. What is the load corresponding to the maximum efficiency? So the condition for maximum efficiency, you know, is maximum efficiency condition is that core losses and copper losses are equal. Now core losses are constant, copper losses are going to be, listen very carefully, X square times PCUFL. Why? Because copper losses you are writing as 3 times I square R, something like this. Now this I is X times I full load. So if you put it, the copper loss becomes X square times PCUFL, where PCUFL is 3 times I full load square into R. Now, for maximum efficiency, the loading X is going to be given as simply PC upon PCUFL. What is this PC core loss? 400. What is this PCUFL? 800 given. So this is 1 upon under root 2. Now, he is asking the load corresponding to maximum efficiency. So load corresponding to maximum efficiency is going to be the loading, and the rated power is given as 50 kVA. So this is going to be 1 upon root 2 into 50. This was volt ampere, so it becomes kVA. So if you solve this, I think you must be getting A as the correct option, 35.33. 35.33 you must be getting as the load corresponding to the maximum efficiency. Is it clear, everybody? Let us see the next question. The next question belongs to, again, the efficiency. A 300 kVA transformer has 95% efficiency at full load and 0.8 power factor lagging. In the second case, it has 96% efficiency at half of the load, unity power factor. He is asking what is the maximum efficiency at unity power factor load. So let us first understand, if you want to write the maximum efficiency, what do you want? You want loading X, yes? The loading for which you are getting the maximum efficiency multiplied by S, that is the rated output, cos phi. This is total power output, yes or no? Because efficiency you are relating with the real power. And denominator, it is XS cos phi, that is the output, plus losses. Now losses are going to be core losses and copper losses. In case of maximum efficiency, copper losses, core losses equal. So it becomes 2 times the core losses. So this is how you are going to write the maximum efficiency. Let us see what are the inputs you already have in this. Do you have the load corresponding to the maximum efficiency? No. Power factor is given as 1. That's good. Do you know S? Yes. S is also given 300 kVA. This is given as 300 kVA. This is given as 300 kVA. But you don't know what is X. And you don't know what is PC. If you know the core losses and full load copper losses, can you write the loading for the maximum efficiency? Yes. So basically there are two unknowns, core losses and the full load copper losses. These two unknowns you have to find. And for finding these two unknowns, the data is given for the efficiency in two cases. So in general, what is the expression for efficiency you are writing? Output XS cos phi divided by XS cos phi plus core losses plus X square PCUFL, full load copper loss, multiplied by 100. Now he is saying the efficiency in the first case is 95%. So it is 0.95. X is the loading. He is saying 95 efficiency at full load. So X becomes 1. What is S? 300 kVA. So 10 to the power 3. What is cos phi? Full load 0.8 power factor lagging. So power factor is 0.8. Divided by 1 into 300 10 to the power 3 into 0.8 plus, we don't know what are the core losses. What is X? 1. So it becomes PCUFL. Say this is equation number 1. Similarly, you can write the equation for the efficiency given for the second case. So for the second case, it is 96% efficiency. Okay. And what is the load? It is half of the load. So X becomes 1 by 2. So it is 1 by 2. S is 300 kVA 10 to the power 3. And power factor is unity power factor. In the second case, it is unity power factor. So it is unity power factor. So it is 1 by 2. This is 300 10 to the power 3 into 1 plus core loss. Now what is X? 1 by 2. So it is 1 by 2 square. And this is PCUFL like this. This is equation number 2. So 2 equations, 2 unknowns you have. You have to solve the value for PC and PCUFL. I have the reference, so I will give you the values. Later on, you can confirm these values. PC you must be getting. That is the core loss as per my reference, 4.12 kilowatts. 4.12 kilowatts. And what is PCUFL? What is PCUFL? It is 8.51 kilowatts. 8.51 kilowatts. Okay. Now, the moment you get these two values, can you tell me what is the loading for maximum efficiency? Yes, it is PC upon PCUFL. This is 4.12 PCUFL 4.51. Sorry, 8.51. If you solve this, as per my reference, you must be getting X as 0.696. 0.696, you can cross check it. The moment you get the X value, you know what is the PC, you know what is PCUFL, and even you don't know what is PCUFL, because you are writing the maximum efficiency, you only need the core losses. So you can write the maximum efficiency now. What is the loading for maximum efficiency? Just now you have solved 0.696. It is 0.696 multiplied by 300 10 to the power 3. Power factor is unity. It is given to find the maximum efficiency at unity power factor load. So 1. 0.696 into 300 10 to the power 3 into 1 plus 2. What is PC? Core losses, 4.12 kilowatt. 4.12 kilowatt. Just solve this. This is your efficiency. And multiply by 100 also. Okay, so as per... Okay, just confirm whether it is clear, audio visual, I think not buffering. So as per my reference, you must be getting 96.2% as the final efficiency. 96.2% as the final efficiency. Let's cross check these values later on if you're not doing it right now. Is it clear? Anyways, see the next question. A 50 Hz transformer having equal hysteresis and eddy current losses at rated excitation is operated at 45 Hz at 90% of its rated voltage compared to rated operating point. The core losses under this condition is. Whenever you are dealing with the core losses, so you know that core losses are nothing but hysteresis losses and eddy current losses. Hysteresis losses are KH Bm raised to the power 1.6 F. This is KE Bm square F square. Whenever you are dealing with the eddy current losses, you are telling B for which? Okay, for this. You're not getting 96.2, Ashok. Okay, I think you must be getting 90. C as the correct option. Just cross check it. Cross check it. Okay. So whenever you are dealing with the hysteresis or eddy current losses, core losses, you always cross check about the V by F ratio. What is happening with the V by F ratio? Because this V by F ratio is directly proportional to BM. If V by F ratio comes out to be constant, then question becomes very easy for you. Now you see in the question he is saying it is operated at 45 Hertz at 90% of its rated voltage. So let me find V2 by F2. Voltage he is saying is 90% of its rated voltage. So it becomes 0.9 of V1. Frequency in the second case is 45 Hertz. This is 45. Okay. Now what is V1 upon F1? This is V1. Okay. What is F1? F1 is 50. So if you solve this, it is the same thing. It means V by F ratio in this case is a constant. When the V by F ratio comes out to be a constant, now you can smile a little bit because BM is going to be constant. And the moment BM becomes constant, this all is constant. And you can say hysteresis loss is directly proportional to frequency and eddy current loss is directly proportional to the square of the frequency. This is how you can write it. Suppose in the first case, the core losses are hysteresis loss and eddy current losses like this. But he is saying in the first case, the transformer have equal hysteresis and eddy current losses. If it has equal hysteresis and eddy current losses, that is PH1 is equal to PE1. So it becomes suppose 2 times PH1 or you can write 2 times PE1. In the second case, suppose the hysteresis losses are PH2 and the eddy current losses are PE2. So can you compare PH2 and PE2? Yes. PH2 upon PH1, because hysteresis loss is directly proportional to frequency, so it becomes F2 upon F1. F2 is 45 Hertz, F1 is 50 Hertz. So PH2 you can find it is going to be how much? Okay. Simplify this. I think it is going to be, if you multiply by 2 both the sides, so it becomes 0.9 PH1. Similarly, can you write it for eddy current losses? Eddy current losses are going to be F2 upon F1 whole square. This is PE1. F2 is 45. This is 50 to the square. So it must be coming at 0.81 PE1. So now if you find PC2, PC2 is going to be, PH2 is 0.9 PH1 plus it is 0.81 PE1. If you add these two, okay, so it becomes 1. 9 8 17 के साथ ऐसे लगेगा 1.71 PH1 you can say, because PH1 PE1 are same. Okay, PH1 PE1 are same. So the changes in the core loss is going to be 2 PH1 minus 1.71 PH1 divided by 2 PH1 multiply by 100. If you solve this, as per my reference, it must be coming around 14.5%. Okay. Data खत्म हो गया था, that's why. My God. Now it is okay. If you want me, I can recharge your mobile, okay? But first you have to send me money. Okay? 1 lakh rupees directly you can recharge. Anyways, just joking. So you must be getting it somewhere. So it is reduced by 14.5%. So what is the correct answer? C is the correct answer. Is it clear, everybody? Let us see the next question. The percentage resistance and percentage reactance of a 10 kVA 400/200 volts three-phase transformer are given as 2% and 10% respectively if the constant losses in the machine are 1%. Constant losses in the machine are 1%. It means what? PC is given as 1%, core losses. Okay. And percentage resistance is given as 2%. So percentage resistance of the transformer is nothing but the full load copper losses. That is the same thing. You must be aware with this, 2%. He is asking what is the maximum possible percentage efficiency of the transformer. Now you know that if you want to write the maximum efficiency, it is given as XS cos phi upon XS cos phi plus 2PC multiply by 100. Now there is no information given for the power factor at which you will be finding the maximum possible efficiency. Now in this case, you can take the power factor as unity, because unity power factor will always give you the maximum possible efficiency. Now, the only thing you have to find in this question is X. So it becomes XS upon XS plus 2PC. Story is over. What is X? Sorry. Yes. If you know PC and PCUFL, can you tell me what is X? Yes. It is PC upon PCUFL. So if you put the values, what is PC? 0.01. What is PCUFL? 0.02. It is going to be 1 upon root 2. You can solve it. Just put this value here. So what is going to be maximum efficiency? It is X, that is 1 upon root 2. I am writing in per unit. What is S? 1. Power factor is 1. This is 1 upon root 2. 1 into 1 plus 2PC, because PC is given in percentage per unit. So I am writing in per unit. PC is given as 1%. So this is 2 times 0.01 multiplied by 100. Just solve this, you will get the efficiency. Maximum possible efficiency, as per my reference, it must be coming as 97.27. Okay, are you getting this? 97.27%. Just cross check this value. So approximately you can say C is going to be the correct option. C is going to be the correct option. The next question. Okay. Next question again belongs to the short circuit test. Instruments connected to the high voltage side, short circuit test readings for a 50 kVA 24/240 volts transformer are given as 48 volts, 20.8 amperes and 617 watts. Now, you can use one formula I am giving you, that you can write Z equivalent directly. This is going to be VSC, this is going to be ISC, okay, and the angle for this Z equivalent is going to be cos inverse PSC upon VSC ISC. Okay, you can write this formula direct so that you can get Z equivalent if you know all the three values. So just put up the values, see what you are getting. You remember the circuit, na? If you know the circuit, you can write it very easily. What is VSC? 48. What is ISC? 20.8. This is cos inverse. What is PSC? 617 watts. 617 watts. This is 48. This is 20.8. within one line the story is over. So if you solve this, as for my reference, so I don't have a reference, you have to solve it. Okay, so you can find what you are getting Z equivalent, that you can write as R equivalent plus X equivalent, real and imaginary part. You will get all the values. If you cross check this, I think there is also a multiple select question. Okay, so you must be getting R equivalent, Z equivalent and X equivalent, all these values. Just cross check these values. This is one shortcut way of doing the same problem that we have done earlier. Okay. Now next question also belongs to efficiency. Okay, but it is a little interesting question. It is a good question. See the question. Maximum efficiency of 500 kVA 3300/500 volts 50 hertz transformer, single phase transformer is 97% at 75% of the full load at unity power factor. If the transformer impedance is 10%, okay, calculate the regulation, that is the voltage regulation at 0.8 power factor lagging. So let me tell you, the voltage regulation of the transformer approximately you can write as Z equivalent cos of theta equivalent minus phi. So if you want to write the approximate value for the voltage regulation, you must be knowing the Z equivalent of the transformer, theta equivalent, that is the impedance angle of Z equivalent, and what is the power factor at which you are finding the voltage regulation. Let us see what is the unknown here. The first thing is Z equivalent is given. Yes, the transformer impedance is given as 10%. So it becomes 0.1 because it is given in per unit. Now cos theta equivalent given. Theta equivalent is not given because you know the total transformer impedance, but you don't know what is the R equivalent and X equivalent. So we don't know this theta equivalent. What is phi? Phi is given. Yes, phi is given. 0.8 power factor lagging. So this is theta equivalent minus phi is 36.86. That is the cos inverse 0.8. So anyhow, if you can find theta equivalent, you can find what is the voltage regulation that is asked in the question. Now, why he is giving you this this efficiency data? What is the reason? The reason is basically you know Z equivalent. What is Z equivalent? It is R equivalent plus X equivalent. So any two values, if you know, third value you can easily find. Z equivalent you know. If you can find what is R equivalent, so you can very easily get what is theta equivalent. Now this R equivalent is nothing but it is equal to the full load copper losses. How you are going to find the full load copper losses? You know X is under root PC upon PCU FL. You know what is this X value? Yes, it is mentioned. Maximum efficiency of a 500 kVA 3300/500 volts 50 hertz single phase transformer is 97% at 75% of the full load. So X is already mentioned here. So X is 75%. You want to know what is full load copper loss, but you don't know what is PC. Now this PC you are going to find with this efficiency condition. Maximum efficiency is XS cos phi upon XS cos phi plus 2PC. What is maximum efficiency? 97%, 0.97. What is X? 75%, 0.75. What is S? Now, wait. Because he is giving you in percentage, so better you write it in per unit only. Yes, better you write in per unit only. So this S is going to become as 1. this S is going to become as 1. And what is cos phi? It is given as 0.8. It is X is 0.75. This is 1, this is 0.8, plus this is 2 PC. You just find what is the value you are getting for PC. Okay. As per my reference, you must be getting PC as 0.116 per unit. 116 per unit. You know what is PC? You know what is X for the maximum efficiency? What is the loading? Can you find PCUFL? Yes. So PCUFL is going to be PC upon X square. What is PC? 0.0116 divided by X square. This is 0.75 whole square. Just solve this, you will get the full load copper loss. This you must be getting as 0.206. 0.206 per unit. The moment you get full load copper loss, this is nothing but R equivalent, that is per unit, PCUFL, that is 0.206. Can you tell me what is theta equivalent? Yes, it is cos inverse R equivalent upon Z equivalent. Because cos theta is R by Z. So this is cos inverse. What is R equivalent? 0.206. What is Z equivalent? 10%, 0.1. Let's solve this. As my reference, I think you must be getting it somewhere around 78.11 degrees. 78.11 degrees. Just cross check it. 78.11 degrees. Okay. So now you can solve it, the voltage regulation within one go. You put all the values, that is Z equivalent cos of theta equivalent minus phi. This is the similar expression that you have R per unit cos phi plus X per unit sin phi. It is more compact, okay? It is more compact. That is the reason, if you want, you can use this also. So Z equivalent is 10%, so it is 0.1. Cos of, what is theta equivalent? Just now you have solved, 78.11. And what is phi? 36.86. So if you solve this, somewhere around 7.52% you must be getting. 7.52% you must be getting as the voltage regulation. So A is the correct option. A is the correct option. Is it clear for everybody? Just tell me yes or no in the comment section. Everybody is getting that? Okay. The next question is also important this year. This type of question. The question based on all-day efficiency. Generally, we are calculating the all-day efficiency or energy efficiency for distribution transformers. The reason is for distribution transformers, the primary is always on. The primary is always switched on. Yes or no? Distribution transformer, because the power system people, they don't know when you are going to switch on your light, AC or load. So all the time the primary should be energized. So it means the core losses are happening all the time throughout the day, 24/7. And that is the reason distribution transformers are such designed so that they have less core losses comparatively. But for defining the efficiency of distribution transformers, we are using the concept of all-day efficiency or energy efficiency to know their performance, where time factor is also involved. So all-day efficiency is defined as the output kilowatt hour in 24 hours, because day is there na, all day, and divided by output kilowatt hour in 24 hours plus core losses multiplied by 24 hours plus copper losses yes, multiplied by 24 hours. Not actually 24 hours, because it is going to be different for different time. So yes, total copper losses. You understand it like this only, okay? You understand it like this only. Multiply by 100. This is how we are writing the energy efficiency or all-day efficiency. Is it clear, everybody? Now you see, in the starting of the problem, he is giving you some data. 500 kVA transformer has maximum efficiency of this. Now, why he is giving you this data? Please tell me. He is giving you for 6 hours, it is loading is 300 kVA, 0.8 power factor lagging. Okay. 4 hours, this is the power output, 0.6 power factor lead. For 5 hours, no load. For 9 hours, 225 kVA unity power factor, this and this. Throughout the question, he is not giving you what is the core loss. And you require core loss to write the all-day efficiency, yes or no? 24 hours, you have to multiply. It means the data which is given in the starting of the problem is nothing but to give you an indication of the core losses. So write the maximum efficiency first. It is XS cos phi divided by XS cos phi plus 2PC. What is maximum efficiency? 98.6%. So 0.986. X is the loading that is given as 350 kVA. So what is X here? Loading is 350 upon 500. Okay. So this you can write as 350 upon 500, or directly you could have written 350. What is power factor? Unity power factor. Unity power factor. So it becomes 1 divided by 350 upon 500 multiply by 500 plus 2PC. Now from here you can find what is the core loss. As for my reference, you must be getting somewhere around PC, you must be getting as 2.4848 kilowatts. 2.4848 kilowatts. Okay. Now you know the value of core losses. Can you tell me what is the value of copper loss? Yes. Full load copper loss is going to be PC upon X square. What is PC? Core loss. 2.4848 kilowatt. What is X square? X is 350 upon 500 whole square. Just solve this. As per my reference, you must be getting the full load copper loss as 5.07. 5.07 kilowatts. This was what? Because you have multiplied 10 to the power 3. Now, whenever you are solving the problem for all day efficiency or energy efficiency, always first you find the core losses, that is a constant, and find the full load copper loss. Because for the different loading conditions for different hours, you have to find what is the copper loss. Okay, so once you know the full load copper loss, for any loading you can find what is the copper loss. So let us take the first duration, 6 hours. So 6 hours duration. What is the output? What is the output? Output is given as 300 kVA. Now this 300 kVA multiplied by 0.8, that is the power factor. That is the power factor you have to multiply. Then you will get the real, because we are interested in the real power. Yes, copper loss is nothing but the real loss. So 300 kVA multiplied by 0.8, that will give you kilowatts, na? Okay. So this is the output multiplied by 6 hours, because it is for 6 hours. So this you will be getting as kilowatt hour. Is it clear, everybody? Now, what is the copper loss during this time? Let us understand. You have the full load copper loss, yes or no? So if you know what is the loading for these 6 hours, you can write the full load copper loss, yes or no? What is the loading? The loading is 300 kVA. So 300 divided by 500, this is X loading square into PCUFL into how many hours? 6 hours. So it is 300 upon 500 whole square. What is full load copper loss? 5.07 multiplied by 6. This again becomes kilowatt hour. Are you getting that? So this is the story for 6 hours. For next 4 hours. 4 hours. What is the output? Output is 240 kilowatts. So directly he is giving you 240 kilowatts. No problem. 240 kilowatts directly he is giving you. So it is 240 kilowatts multiplied by the number of hours 4. It becomes kilowatt hour directly. What is the copper loss during these hours? Now understand, what is the loading? Now when MVA was given, kVA, when volt ampere was given, directly you were able to find out what is the loading, 300 divided by 500. But in this case, he has done a little bit of twist. Instead of giving kVA, he is giving you kilowatt. So how you are going to write kVA? Kilowatt divided by 0.6. Yes or no? So it is going to be something like this. If you know the concept, you can understand. It is 240 divided by, what is the power factor? 0.6. It is 0.6 divided by 500. This is the square you have to do and multiply by full load copper loss, that is 5.07. 5.07. Number of hours 4, and this is kilowatt hour. How many people are getting this? It is a very simple thing, but you may find it a little difficult in the pressure of the examination. Okay. Next 5 hours, no load. And I told you, even if there is no load, core losses will happen. So core losses will be happening all the time. All the 24 hours, core losses will be happening. Next is 9 hours. Now you can solve for 9 hours. Let me add some pages here. Let me add some pages here. For 9 hours, duration, what is the power output? Power output is mentioned as 225 kVA. So it is 225 kVA multiplied by 1 because it is unity power factor multiplied by number of hours 9. This is kilowatt hour. What is the copper loss? Again, loading is given as 225. So it becomes 225 divided by 500 to the square. Full load copper loss 5.07. 5.07, number of hours 9. This is kilowatt hour. Okay. Now I want to know what is the total power output in terms of kilowatt hour. Now you have to tell me what is the total power output in terms of kilowatt hour, because we have to find the energy efficiency, so we are talking in terms of kilowatt hour. Now what you have to add? For 6 hours, this one. 4 hours, this one. 9 hours, this one. Because 5 hours, it is no load. Okay? So you write it. What is the total copper losses in terms of kilowatt hour? Understand again. For 6 hours, you have to add this. For 4 hours, you have to add this. For 9 hours, you have to add this. 5 hours you will not include because core losses will happen during no load, but copper losses will not happen. So you can find this also. What are the core losses? Kilowatt hour. You know the core losses are constant losses. Core losses you have just found 2.4848 kilowatt. It is 2.4848 kilowatt multiplied by 12. Okay, multiplied by 12. This is kilowatt hour. Now you can put all the values and you can get what is the energy efficiency or all the efficiency you are getting. As per my reference, you must be getting somewhere around 97.95. 97.95. Let me tell you what are these values, okay, so that you can match your result. What is total output? Okay, but I'm not getting it. I don't have a reference. Sorry, you have to solve it. I can give you the final value. That is 97.95%. So as for my reference, you must be getting 97.95. Just cross check this whether you are getting this or not. Take your time, put the value and cross check it. Take your time and confirm these values. Now, what I see the fluctuations in the number of candidates live in the class. Some people are coming to the class. देखे भाई क्या चल रहा है, थोड़ी देर देखा, कुछ मजा नहीं आ रहा है, क्या हो रहा है, फिर चले गए कहीं घूम घाम के आए, थोड़ा दोस्तों से बतिया के आए, इधर उधर कुछ कर लिया, फिर आ गए. Now you are at this age, you should not be driven by your mind, rather you should give instruction to your mind. Whatever your mind is saying, just do the opposite. You will be successful in life. For next 3-4 years in your life, whatever your brain is saying, okay, let us sleep, let us talk to friends, let us go here, let us go there, just do the opposite for next 3-4 years. Okay, Challenge your limits, challenge your capabilities. Anybody is getting this? Yes, everybody? Oh my God. So that's a great thing. All your doubts are cleared. That's a great thing. So I hope you must be getting this. Let us talk about this question, open delta connection. A three-phase 1000 kVA 0.86666 lagging power factor load is supplied by a V connection. V connection is actually open delta connection. Open delta connection. Open delta connection. He's asking determine the kVA output and power factor of each transformer. Please understand the basic idea about the open delta connection. Suppose this is a delta connected transformer. I am not writing separate for the primary and secondary because it is a transformer. It must be written in terms of primary and secondary. I am just writing for one winding. I hope you understand the logic. Now suppose one of the phase winding is opened because of some reason. Maybe there is a maintenance, maybe there is a repair, maybe there is a fault because of some reason. So suppose now what you have is something like this. Okay. Now, what I'm going to give you as a logic is, suppose this is A, this is B, this is C. Okay. So here suppose line current is IA, or because it is acting as a load, suppose this is IA. Okay. I'm just giving you some basic idea. This is IB and this is IC. Now suppose here you are having IAB, IBC, ICA. Okay, how much idea I'm going to give you, you will be able to solve the problems at least, okay? Because complete theory obviously we cannot discuss. Now in case of delta connection, the line current is going to be √3 times the phase current. Hello? Are you getting this or not? Line current is √3 times the phase current in proper delta connection. When one of the phase is open, suppose this AB phase is open. When this phase is open, what is happening? This is A, this is B, this is C. So suppose this is IA, this is IB, and this is IC. Now just take the reference of this phase A and phase B, because only two phases are present now. The third phase is gone. Now you understand the same line current and phase current became similar. Yes or no? Now here the line current was √3 times the phase current. Okay. So you can say IL is √3 times I, whereas here the line current is going to be same as the phase current, that is simply as I. I hope you are getting this. So if for this delta connection you are writing the power as √3 times V and I, where V and I are the line RMS values for three phase. Okay. Then for open delta connection, it becomes √3 voltage. Now current, this line current has become phase current. So write phase current value, that is I divided by √3. So it becomes VI. So if you want to compare the power output of open delta and delta connection, it becomes VI, it becomes √3 VI. So it becomes 1 upon √3 times, which is somewhere around 0.577. Okay. So somewhere around 57.7% of the output, this open delta connection is going to function. With reduced capacity, it is going to function. Now if you want to write the A phase and B phase powers, then you can write it as VI angle phi minus 30, and for B phase it is VI angle phi plus 30 degree. Now phi is given in the problem. What is phi? Phi is 0.866 lagging. So cos phi is 0.866. So phi becomes 36.86 degrees. You know what is phi, okay? And you know the voltage also, okay? Voltage becomes 400. Okay, directly you can write in terms of power itself. Okay, directly in terms of power itself you can write, because the delta connection total power is given. So you can do it 1 upon root 3 times. You can do it simply 1 upon root 3 times. Okay, power for the open delta connection, it becomes 1 upon root 3 times for the delta connection. Okay, so SA and SB directly you can write as 1000 divided by under root 3. Angle phi becomes 30, sorry, cos phi is given as 0.866. Sorry, it is not 36.86 because it is a very close value they have taken. Okay, 8.666. So approximate we cannot take. If you solve it, I think phi you must be getting as 30%. Sorry, 30 degree. Just put it here. So it becomes 30 minus 30, and it becomes 1000 upon under root 30. This is 30 degree plus 30 degree. So finally SA and SB you must be getting 577 angle 0 degree, and for B phase it is 577 angle 60 degree. Is it clear, everybody? Is it clear? See, whenever you are getting a question on this, you can better start from this understanding, and you can write these two equations. Most of the time you will be able to solve the problems, most of the time. Okay, sometimes they are going to ask questions based on the phasor, but that becomes a little complex. Okay, so that will take a bit of time. So if you have the theory, you can revise that. Otherwise these equations are going to be sufficient. So let us see the last question for this. Okay, last question for transformers. Two single phase furnaces A and B are supplied at 80 volts by means of a Scott connection from a three-phase 6600 volt system. The voltage of furnace A is leading. The furnace take 500 kilowatt and 800 kilowatt respectively. Calculate the line current on three-phase side. So see, Scott connection basically you are using it provides connection of two-phase load to a three-phase system directly. So what is the basic idea here? So this is your A terminal, okay, this is your B terminal, this is your C terminal. Okay, this is one phase and this is another phase. So two phases you are going to supply the load. Now this is called as this is called as main transformer. This is the main transformer. This is the teaser transformer. This is the teaser transformer. The number of turns, here it is N1 by 2. Here it is N1 by 2. So total it is N1 and this is having N2. This is having N2. Now the number of turns for this teaser transformer primary is root 3 by 2 N1. Okay. You have to remember this, root 3 by 2 N1. I hope it is clear for everybody. Okay. Now suppose this is current coming here is IB. Okay. And current coming here is IA. One thing. Now understand, suppose the current coming from here is IB. Sorry, it is IA. It is IA. IA current is coming from here. IA current coming from here is going to be divided as IA by 2 and in this direction IA by 2. Yes or no? Now the current between B to C terminals is going to be IBC. So this current is going to be IBC. So can you tell me what is going to be IB? IB you can write as, see very carefully, IB you can write as IBC minus IA by 2. IBC minus IA by 2. And what is IC? IC is going to be IBC and IA by 2, both are coming opposite to IC. So it becomes minus IBC minus of IA by 2. So IA, IB, IC, this is what you have to find. IA, IB, IC, this is what you have to find. Is it clear, everybody? Just tell me yes or no in the comment section. Now, the first thing you have to do is, as per the loads connected to the two phases, okay, it is given that furnace A is leading and the furnace takes 500 kilowatt. So this is going to be for A furnace, this is going to be for B furnace. 500 kilowatt, this is suppose 500 kilowatt at unity power factor. And for the second furnace, it is 800 kilowatt, 0.7 power factor lagging. So it is 800 kilowatt, 0.7 power factor lagging. Can you find IA and IB? Yes, you can find IA and IB. So IA is going to be 500 kilowatt, okay, unity power factor. And what is the voltage given? Voltage given is 80 volts, okay. Furnace A and B voltage are supplied at 80 volts. So this is going to be 500 kilowatt. So it is divided by 80 and unity power factor. So this is what you are getting, IA. Okay, sir. And IB, you can write with this 800 kilowatts and the voltage is 80. And what is the power factor? It is 0.7. It is 0.7. Just find these two values. As per my reference, you must be getting IA, you must be getting as 6250. This is 6250 and IB you must be getting as 14285, 14285.71, 0.71. Now you have to write the phase angle also for IA and IB. Okay. So in the question, okay, so it is unity power factor and it is leading. See, two information given. The voltage is, let me just see it. Yes, voltage is leading and it is unity power factor. So angle is going to be minus 90 for the current. So it becomes minus 90 for the current. This is going to be cos inverse minus cos inverse 0.7. So this is how you can calculate. For IB, as per my reference, you must be getting it 14285, 14285.71, and the phase angle is going to be minus 45.57, minus 45.57. Okay, 57 degrees. The moment you get IA and IB, can you tell me what is IA? Yes or no? IA you can reflect by this IA current. So let me add some pages here. Let me add 2-3 pages here. Okay. So if you have this current I small a, can you tell me what is I capital A? You know what is the number of turns ratio? Yes or no? So what is N1 upon N2? First you find what is N1 upon N2. What is N1 upon N2? See what is the voltage ratio is given. It is 6600. Okay, 6600/80. Let me just confirm it. It is 6600/80. Okay, so N1 is to N2 is going to be 6, because primary side it is 6600 upon, and secondary side, load side, it is 80. So if you find it, it becomes 82.5. Now this is the turns ratio for the main transformer, and for the teaser transformer it is √3/2 N1 is to N2. So just put the values. This is it is 82.5. If you solve this, for the teaser transformer turns ratio, you must be getting 71.45. 71.45. So what is going to be line current IA? It is going to be I small a divided by a teaser transformer. Okay, because this is teaser transformer turns ratio you have to use here. For main transformer, IBC you will be getting, for this complete winding IBC you will be getting. So IBC you will be getting as IB divided by main transformer turns ratio. So if you put the values, I capital A, as per my reference, you must be getting 87.47. 87.47, angle is 90 degree, and IBC you must be getting as 173.16. 173.16, angle is minus 45.57, minus 45.57 degrees. Now if you have IBC, if you have IA, can you calculate what is IB and IC? So you know what is IA, IB and IC. As per my reference, I am giving you the values. You can cross check it later on. IB you must be getting 206.67. 206.67. Angle is 54.07. Angle is 54.07. Okay, there is minus. IC you must be getting 145.19. 145.19. Angle is 146.6. 146.6 degrees. Is it clear, everybody? You just go through this question because this was a little tricky question. If you don't know what is Scott connection, then it will be a little tricky for you how to solve this. So this was the end of the transformer for us, and now we are supposed to discuss induction motor. Okay. Is it clear, everybody? Are you able to follow this? Just tell me yes or no. This open delta connection and Scott connection, it belongs to three-phase transformers. Okay. So you can understand, because of the limitation of time, we cannot discuss each and everything. But if you want to revise it quickly, I have already taken a session on transformer connection. If you want, I can send you the link in the Telegram channel. You follow just this Telegram channel. Okay, Electrical by Ashutosh Saxena. Okay, you will get the complete understanding of three-phase transformers. You can follow those sessions. So anyways, let us now start with the induction motor. Some idea I want to give you for induction motor before we proceed. So friends, if you talk about induction motor, specifically we are talking about three-phase induction motor. Okay, three-phase induction motor we are talking right now. So like any other motor, it has two parts, stator and rotor. Yes or no? Now stator is going to have a three-phase distributed winding. Okay. When you come to the rotor, there are two types of rotors possible for three-phase induction motor. The first one is squirrel cage. Okay. And the second one is wound rotor or slip ring induction motor. तो दहेज में जितनी भी चीजें आती हैं, इलेक्ट्रिकल अप्लायंसेज आते हैं, उसमें ज्यादातर में आपका स्क्विरल केज इंडक्शन मोटर लगा होता है. इसीलिए आप देखिए दहेज में मिली जो वॉशिंग मशीन होती है वो काफी सालों साल चलती है, और जब आपकी शादी हो जाएगी तो आपको पता चलेगा कि वो वॉशिंग मशीन वो एक बहुत बड़ा मुद्दा बन जाती है आपस में लड़ाई का. Anyways, so I'm just joking, take it lightly. But what I wanted to tell you so that you can remember is that squirrel cage induction motor, you can understand majority of the induction motors, they are squirrel cage induction motor because they are robust and rugged in construction. How much difficult circumstances it is going to give you excellent running condition. Okay, excellent running condition. Wait a moment. So this is the basic idea. You have a stator. A stator is going to have a three-phase distributed winding. Okay, and rotor is squirrel cage also possible, and wound rotor or slip ring induction motor also possible. So okay, so it is coming here now. Anyways, suppose this is your stator. Okay, this is your stator. A stator is going to have three-phase balanced supply. This is A, this is B, this is C. So there is a three-phase balanced supply. Thank you so much, sir.
50 floor में machine खराब है, second floor से.
Ayes.
Disturb हो जाएगी.
Sir, I got, Negi sir got me a coffee. Thank you so much, sir. So he is with me right now. Great faculty for civil engineering. Anyways, thank you so much, sir.
Welcome.
So guys, for you. Anyways, I think so this coffee is going to cost me like anything because it is valueless, na?
This 50 ml coffee will going to cost you 750 ml.
Anyways, so if you can come and sir, okay. See, electrical guys also, they are a big fan of you, sir.
Thank you. So nice of you, everyone.
Better you come, sir, na? Just once.
Okay, sir. Thank you.
So guys, give sir a big round of applause. I also learn and get motivated from him number of times.
Okay. Sir, this is electrical machine.
मशीन चल रहा है सर.
Okay.
अभी एक मशीन खत्म हुई है ट्रांसफार्मर, अभी इंडक्शन चल रहा है, फिर कल आशु सर जो है वो डीसी और सिंक्रोनस लेंगे.
Okay. नहीं ये सर जिंदाबाद. So machine starts like boo 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 boo.
सर वो अभी मैं इंडक्शन में बताने जा रहा हूँ. 3 इडियट का एग्जांपल मैं देता हूँ इसमें.
This circle you made?
यस सर.
Okay, very perfect circle, sir.
सर मशीन का फैकल्टी अगर सर्किल ना बनाओ
So this is machine or some coil oil?
No, this is actually core. This is the stator core. अभी इसके अंदर सर एक और पार्ट आएगा, that is a rotor, that is a rotating part. This is the stationary part.
Okay.
अभी सर मैं एक्सप्लेन करूंगा, आप तो यहीं पर है.
Okay. Of course, sir.
तो मैं थोड़ा थक गया था, सीरियसली बता रहा हूँ, बट सर को देखा मैंने और बिल्कुल जोश आ गया मुझे, क्योंकि अभी सर ही मुझे बता रहे थे, शायद लास्ट वीक की बात है, 10 घंटे सर ने लगातार क्लास ली है.
9 hour 55.
9 hour 50 minutes लगभग.
Two classes.
2 classes.
One of Transformation, one is of Geotech.
So, sir, when I was at your age, I also used to take these classes, but now.
When you was at my age, or when you will be of my age?
No, sir. When I was at your age.
Okay.
Right now also I can take, but some health issues are there, sir. So that is why.
Okay, sir.
So guys, say hi to sir. I think once again, sir has motivated us a lot, and let us continue our
Okay, sir.
session.
Okay, carry on.
Thank you so much, sir. Thank you. Thank you for your motivation, sir. So, guys, I think you also got the boost, energy boost, because Negi sir, he's always full on 100 on 100. So, I was telling you this ABC phases, you are going to supply a 3-phase balance supply. 3-phase balance supply. Okay. So what happens after you apply the 3-phase balance supply? When a 3-phase balanced supply means there is a time displacement of 120 degree. You understand that? Time displacement of 120 degree. So if you are saying the voltage for A phase is Vm sin omega t, so the voltage for B phase becomes Vm sin omega t minus 120, or C phase it becomes Vm sin omega t minus 240 degrees. So there is a time displacement of 120 degree when you are talking about the balance supply. Now this supply is given to a 3-phase 120 degree space distributed winding, 3-phase winding. Now this 120 degree displacement is in terms of the space. Now this will give rise to a rotating magnetic field, of stator. This I am going to call as rotating magnetic field of the stator. And this is a rule. When a 120 degree displaced, time displaced 3-phase balance supply is given to a 3-phase 120 degree space distributed winding, a rotating magnetic field is going to be developed. This rotating magnetic field is going to cut the squirrel cage or the winding of slip ring induction motor, something like this. So this is your rotor, suppose. This is your rotor. This is your rotor. This is your stator. Okay. Now, this rotor, whether it is a squirrel cage rotor or whether it is a slip ring induction motor, it is going to have either bars or the windings. And these bars or the windings, the magnetic field or magnetic flux is going to be linked. Okay. So, magnetic flux linked with rotor windings. One of the most important part of discussion is that induction motor rotor windings are always short circuited. Rotor windings or bars in case of squirrel cage, always short circuited. Always short circuited. When always short circuited, the circuit is complete, so you will get rotor currents. Rotor currents will have their own rotating magnetic field. So this is the rotor rotating magnetic field. The moment you have two rotating magnetic fields, these fields are going to interact and you will get the interaction torque. You will get the torque. This is called interaction torque or electromagnetic torque. Okay, this is called interaction torque or electromagnetic torque. And this is how your induction motor actually starts. Is it clear, everybody? Okay. Now, so if I have to show you the rotating magnetic field of the stator, this is running at the first place. Behind this, you have the rotating magnetic field of the rotor. Okay, so rotating magnetic field of the stator is ahead, rotating magnetic field of the rotor is behind, and because of the interaction of these two fields, this is the rotor rotating at some speed. Okay, now if you see the relation, so you have rotating magnetic field of the stator, you have the rotating magnetic field of the rotor, and you have the rotor rotating at some speed. So if this is a fixed reference, suppose it is the stator or a stationary reference, because the stator is going to be stationary, so this is a stator frame of reference. A stator frame of reference. So rotating magnetic field of the stator is rotating at synchronous speed with respect to the stator frame of reference. The rotating magnetic field of the rotor is also rotating at the synchronous speed with respect to the stator frame of reference, and the rotor is rotating at NR speed with respect to the stator frame of reference. Why? It is a compulsory condition, because for any rotating machine, there should be no relative motion between the two fields. Okay, so here you have the stator field and the rotor field, both are rotating, so there should be no relative motion between them, because if there is a relative motion, interaction torque cannot be developed. It is simple logic. Suppose you want to talk to me, I want to talk to you, so we must be sitting together, na? It's not that I am sitting, you are running, or you are sitting, I am running. So there should be no relative motion between these two fields, and only the uniform torque is going to be developed. So I hope these basic things must be clear for you for induction motor. Let us start with the problems directly. So there is a 4-pole synchronous generator driven at 1500 RPM feeds a 6-pole induction motor which is loaded to run at a slip of 5%. What is the motor speed? The situation is something like this. This is the synchronous generator. This synchronous generator is supplying power to a induction motor. Okay. Now he is saying the synchronous motor is going to have 4-pole. It is driven at 1500 RPM. And the induction motor is a 6-pole machine. And it is running at a slip of 5%. So the slip is 5%. Okay. Now, if you want to write what is the speed at which motor is rotating, directly you can use the formula. Okay. What is the formula? The formula is NR is equal to NS 1 minus S. What is NS? NS is the synchronous speed. That is 120 F upon P. You know what is the number of pole for the induction motor, that is 6, but you don't know what is the frequency. Frequency is going to be decided by the supply. So frequency is going to be decided by the supply, and you can write this F from the synchronous motor. It is Pn upon 120. So number of poles are 4 here. Speed is 1500 divided by 120. 0 0 cancelled. 4 3 12, 3 5 15, 50, 50 hertz. So by default you are getting 50 hertz, but you cannot say that it will always be 50 hertz. So you have to get the calculation right. Okay. In examination, don't assume anything. So put it 50%, 50 hertz. So it is 120 into 50 divided by number of poles are 6. So 6 दूनी 12, 20, 5 दूनी 10, 1000. 1000 RPM आ गया, 1000 RPM. It is 1 minus 0.05. So finally you will be getting 950 RPM. So C is the correct option. C is the correct option. Next. A properly shunted center zero galvanometer is connected in the rotor circuit. Galvanometer is connected in the rotor circuit of a 6-pole 50 Hz wound rotor induction motor if the galvanometer makes 90 complete oscillations in 1 minute. Galvanometer is connected in the rotor, yes or no? So rotor frequency is going to be how much? 90 oscillations in 1 minute. 90 oscillations in 1 minute, that is 60 seconds. So 0, 0 cancel, 3 2 6, 3 3 9, this is 1.5 Hertz. This is 1.5 Hertz. But you know that rotor frequency is slip frequency, slip times the supply frequency. So you can write the slip as Fr upon F. Fr is 1.5, F is 50. The moment you have slip, you can find what is the rotor speed. Rotor speed again you can write is Ns 1 minus S. What is Ns? 120. Frequency is 50. Number of poles are, now this time, 6. 1 minus slip is 1.5 upon 50. So if you solve this, I think you must be getting D, 970 RPM. Is it clear, everybody? You must be getting 970 RPM. So I think let us stop because I think it's not going to be completed even if we go for 1 more hour. So let me make another session for you, okay? And I think you are also feeling exhausted. Because I can see the number of candidates falling drastically. So there is just one candidate answering and he is so desperate, he is asking me to continue. Okay, but it's very difficult. Anyways, let us see how much we can go. Okay. Let us see how much we can go. See the next question. A 3-phase 50 Hz induction motor runs at a speed of 576 RPM at full load. By what factor the rotor resistance be increased for the motor to run at a speed of 528 RPM at full load? So basically he is giving you two conditions of a speed, okay? Two conditions of a speed, and he is asking you by what factor the rotor resistance is to be increased so that the motor runs at a speed of 528 RPM at full load torque. Now if you observe the torque equation of the induction motor in general, okay, you can write it 3 times E2 naught square upon 2 pi ns upon 60. This is slip times R2 upon R2 square plus X2 square. This is the general expression, but you know that S is very small, slip is very small, as the rotor speed is very close or just behind the synchronous speed. So the difference between the rotor speed and the synchronous speed is very less. So slip is a very small value, generally very small value. So you can say, sorry, it is S X2 naught whole square, okay? You can say R2 square is going to be a larger value in comparison to S X2 naught whole square. So if you simplify, your torque becomes 3 times E2 naught square upon 2 pi ns upon 60. This is slip times R2. This is R2 square. So R2 cancelled. So R2 cancelled means what? You can say that torque is going to be directly proportional if E2 naught is not changed, ns is not changed, frequency is not changed, number of poles not changed. It is going to be directly proportional to S upon R2. Now in the question it is given, the first case it is a full load condition. In the second case also he is saying it is a full load torque. It means both the cases he is talking about the full load condition. It means torque is going to be same. In both the conditions torque is going to be same. So you can write S2 upon R22 and this is S1 upon R21. If you can find what is S2 and N1, that is the slip for the two cases, very easily you can find what is the relation between R22 and R21. Now, in the first case, he is giving you the rotor speed as 576 RPM. In the second case, he is giving you the rotor speed as NR2 as 528 RPM. Now, if you know the synchronous speed, very easily you can find what is S1 and S2, but you don't know what is the synchronous speed. How to find the synchronous speed? Synchronous speed is going to be 120 F upon P, okay? You know the frequency is there 50 Hertz, but you don't know what is the number of poles. You don't know what is the number of poles. So number of poles you have to guess. As I told you that the rotor speed is going to be very close to the synchronous speed. So you keep on putting different values. Suppose it is 120, this is 50. You keep on putting different values for P. Suppose you put 10, P is equal to 10. So it is how much? 600 RPM. 600 RPM is just above this full load speed. So you can understand that by guess you can say the number of poles are going to be 10. So if 600 RPM is the synchronous speed, what is S1? It is going to be 600 minus 576 divided by 600. Just find this value. What is S2? S2 is going to be 600 minus 528 divided by 600. Just find what is S2. If you know what is S1, what is S2, you can relate R22 and R221. R22 and R221 are the rotor resistances in the two case, and you will be getting R22 as 3 times R21. Is it clear, everybody? One similar question that you can try. In this question, he is asking you what is the external resistance you are going to add in the rotor circuit per phase. Now, same situation, rotor of a 4-pole 50 Hertz slip ring induction motor has a resistance of 0.2 ohms per phase. So, R2 is given as 0.2 ohms per phase. This is given. Runs at 1440 RPM at full load. So, full load NR1 is given as 1440 RPM. Okay, calculate the external resistance per phase, which must be added to lower the speed. So the second case, NR2, speed becomes 1300. The torque being the same as before. So T2 is equal to T1. Same situation, T2 is equal to T1. So again, S2 upon R22 is equal to S1 upon R21. Yes or no? What is S2? Just see here. If you see the synchronous speed is going to be 120, frequency is 50 Hertz divided by P, that is number of poles as 4. So if you solve this, 4 3 12, it is 1500. 1500 RPM is the synchronous speed. You can find S2 as 1500 minus 1300 divided by 1500. What is S1? It is 1500 minus 1440 divided by 1500. Just put it here and you will be getting R22 as some value R21. Okay, just check what is the value you are getting. Now the external resistance that you have added is going to be, I don't have a reference for this, so you have to solve this. R22 minus R21. R22 minus R21. If you solve this, I think you must be getting 0.465. C as the correct option. 0.465. Just cross check it. R21 is already given, okay, 0.2 ohms per phase, 0.2 ohms per phase. It is already mentioned. Okay, it is already mentioned. So you must be getting 0.465. Is it clear? Okay, little fast I have to go because a lot of things we have to cover. Anyways, a three-phase induction motor has a starting torque as 1.5 times full load torque. So, starting torque, how many times full load torque? It is given 1.5 times. And maximum torque as 2.5 times full load torque. 2.5 times full load torque. He is saying calculate the starting current. Calculate the starting current in per unit. So if you know the ratio of starting torque to full load torque, you can relate as full load slip I starting upon I full load whole square. This is the expression. In the question, he is asking calculate the starting current in per unit. What is the meaning of starting current in per unit? This is I starting divided by I full load. It is what you can call as a starting current in per unit. Is it clear, everybody? So do you have this relation I starting and I full load? Do you have? Yes, I starting, I full load is given. Sorry, T starting and T full load is given as 1.5. So this value is given 1.5. You have to find this value. So the only thing you have to find in this question is the full load slip. How you are going to find? Okay. So you must remember this formula. Full load torque upon maximum torque. The formula is 2SSM upon S square plus SM square. Now in case of full load, if you are going for the starting torque, so starting torque divided by maximum torque is, just put S is equal to 1, because in case of starting of the induction motor, at a starting the rotor speed is 0. When rotor speed is 0, the slip at the starting becomes 1. So if you are comparing the starting torque with the maximum torque, just put in this expression S is equal to 1. So it becomes 2SM upon 1 plus SM square. Now if you see the values, do you have the ratio of starting torque and maximum torque? Do you have the ratio of starting torque and maximum torque? Yes, starting torque and maximum torque. 1.5 divided by 2.5. It is 1.5 divided by 2.5. Solve this equation. Solve this equation, quadratic equation. You will be getting a value for slip at which you are getting the maximum torque. You will be getting a value of slip at which you are getting a maximum torque. So as per my reference, you must be getting the slip at which you are getting maximum torque as 1 by 3. This is 1 by 3. Because it is a quadratic equation, you will be getting one more value for SM, that is 3. So you have to discard it, because it cannot be more than 1. Okay, so you got the SM value. Now this equation you have to use. What is the ratio of full load torque and maximum torque? Full load torque and maximum torque ratio is going to be 1 upon 2.5. So it is 1 upon 2.5 ratio of full load torque and maximum torque. This is 2. S is full load slip. SM is 1 by 3. SM is 1 by 3. 1 plus, sorry, wrong. S plus SM square. What is S? You have to find. Plus Sm is 1 by 3 whole square. You have to find the value of S. Again, you will be getting two values. As per my reference, you are getting two values, 0.06969 per unit. And the second value you are getting is 1.597. 1.597 per unit. So again, this is discarded, more than one. This is going to be your full load slip. Just put this value here. Full load slip 0.06969. You will be getting the value of I starting upon I full load. I starting upon I full load, as per my reference, you must be getting 4.642. 4.642. So what is the correct option? Is it clear, everybody? See the next question. See the next question. A motor is operating at full load with a slip of 3% and synchronous speed of 1800 rpm. It is driving a load whose load requirement is independent of the speed. Very important. Is driving a load whose load requirement is independent of the speed. So torque is constant. It is not depending upon the speed. Torque is constant. Okay. For some reason, the line voltage suddenly drops to 90% of the rated voltage. Determine by what percentage the motor runs hotter or cooler. Now, if you imagine you are sitting in your room and suddenly there is a drop in the voltage, what is the first consequence you are going to observe? You will see what? When there is a voltage drop, the fan speed will be more or less. When there is a voltage drop, less voltage is coming, it is going to be less speed or more speed? If voltage drops, so the rotor speed is going to be reduced. If the rotor speed is reduced, what happens to slip? Slip is going to increase. Slip is going to increase. Now, if slip increases, what about the rotor copper losses? These are slip times air gap power. Now, if you see the air gap power is given as torque multiplied by 2 pi ns upon 60. Now, you are saying torque is constant. Frequency, number of poles, you are not changing. This is also constant. So, can you say the air gap power is constant? Yes, you can say air gap power is constant. Air gap power constant means if the slip increases, rotor copper losses increases. Rotor copper losses increases means what? Heat dissipation increases. Copper losses are nothing but heat dissipation. Heat dissipation increases means what? The temperature of the motor is going to be increasing. This is going to be increasing. This is the complete process you have to understand. Okay. So this question is based on this understanding. Okay. Is it clear, everybody? This complete process. Now, he's asking determine by what percentage the motor runs hotter or cooler. Now you understand one thing. Temperature at which your motor is operating is directly proportional to the heat. Heat is directly proportional to the rotor copper losses. Rotor copper losses are slip times PG. PG air gap power is constant. Just now you have seen So can you say it is directly proportional to slip? So can I say the temperature is directly proportional to slip? Yes or no? So basically I have to find the slip in both the cases, and by comparing the slip I can find whether there is a temperature rise or temperature drop. What is going to be the slip in the first case? A motor is operating at a full load slip with 3%. So the starting slip already he is giving you 3%, 0.03. Okay. Now you have to find the slip when there is a voltage drop to 90%. Now please understand. I told you the torque equation is 3 times E2 naught square upon 2 pi ns upon 60. This is SR2 upon R2 square plus slip times X2 naught whole square. So because slip is going to be a small value, you can neglect this term. R2 cancelled. Now this E2, listen very carefully, E2 naught is directly proportional to the supply voltage. Is directly proportional to the supply voltage. This is the EMF induced per phase of the rotor winding. Yes or no? What is E2 naught? At a standstill. Okay. So it is directly proportional to the applied voltage. So can I say torque is directly proportional to slip voltage square? Yes or no? Now you are saying, sir, constant, torque is constant. Torque constant means what? Let me do it here. Torque constant means what? T2 is equal to T1. So you are saying, sir, S2 V2 square is S1 V1 square. Yes. So what is S2? It is S1 V1 upon V2 whole square. S1 is 0.03. This is V1. V2 is 0.9 V1. This is what you find as slip for the second case. As for my reference, you must be getting the slip for the second case as 0.037. 0.037 you will be getting. The moment you get the slip for the second case, the problem is over. You have to find the change in the temperature. Okay, so it is directly proportional to slip. So initially slip was 0.03. Now it has become 0.037. So you can write it as 0.037 minus 0.03 divided by 0.03 multiplied by 100. This is the second case minus first case. Just solve it. You are getting a positive value. Positive value means there is an increase in the temperature. If you solve it, as per my reference, you must be getting around 25%, nearby 25% hot. Your motor is going to be 25% hot, and that is the reason when there is a dip in the voltage, the speed is reduced, but at the same time the heat or the temperature of the motor is going to be increasing, and if it is not disconnected from the supply, there is a possibility the motor is going to damage permanently. So it is A option. Is it clear, everybody? Okay, so let us stop here and let me plan another session, because I have to do a lot of problems for induction. It's not going to be completed. Lot of areas I have to compare. So complete I have to. So just stop here and let us plan one more session. I am planning one extra session for power system. Similarly, we'll be planning one more session for machines, because you understand it is a large subject. It requires some amount of time. Okay, so let us stop here Thank you so much for joining me live in the discussion. There are some more problems that needs to be discussed, but it will take some time, and I want to discuss some more concepts. Okay. Ashu sir is not going to join today. He is going to continue in the tomorrow's session. Tomorrow 4 onwards, he is going to be there. I will not be there. Okay. So whatever remaining topics are going to be there, we will plan one more session and we will try to finish up with that. Okay. So thank you so much, friends. If you have not subscribed to BYJU'S Exam Prep, so scan this code so that you can subscribe to BYJU'S Exam Prep app and the Telegram channel. My topics were only transformer and induction. DC and synchronous is going to be taken care by Ashu sir tomorrow. Okay. Any more doubts, you can always reach out to me. So let me plan one more session for machines also. Okay. So thank you so much, friends. It was nice talking to you. I hope you enjoyed the class. You learned something, and my best wishes are always with you. And Team BYJU'S Exam Prep is always going to be with you throughout the examination process. Thank you so much. Stay connected. Thank you. Thank you. No. Don't worry. I will send the PDF. Okay. Just after the session, I'm going to send both the PDFs, power system also, and machines also. Thank you so much. Take care. Thank you, everybody. Thank you.